This program is brought to you by Stanford on iTunes U at Stanford University. Please visit us at itunes.stanford.edu.
They behave oddly. I've showed you some. Interference of light waves when they go through slits and that sort of thing. Uncertainty principles for particles, and a photon is a particle, so it shares the uncertainty principle with other particles. But perhaps the really simplest context, the simplest system for studying the basic fundamental difference between classical thinking and quantum thinking is the polarization of a photon. If we forget everything else about the photon, assume that it's going in a particular direction, let's say down the z-axis, with a very specific momentum, then the only thing that's left to discuss about the photon is the direction in which it's polarized. That polarization, degree of freedom, forms a kind of mini quantum system that has more insight in it, I think, or more insight can be gained from it than I think thinking about almost any other simple quantum mechanical system. So I want to go through, we started it last time, I want to continue, but first I want to review a little bit. First of all, how should you think about the polarization of the photon? Well, the photon is going into the blackboard. All right, so we need not worry about its direction of motion. We need not worry about its momentum. We need only worry about this little vector, this sort of little flag that the photon carries with it. It moves into the blackboard. Let's see, that's a bad color, isn't it? It moves into the blackboard. That's an even worse color. I didn't bring my own this time. I tell them every time to please leave me pens. The photon is going into the blackboard. Good. And we can think of the plane perpendicular to the motion of the photon. And in that plane, there's a kind of little flag. The little flag can point in any direction in the xy plane. The photon's moving in the z direction. This is the xy plane, x and y. And in a certain sense, to be specified, and only to be correctly defined when we think about it quantum mechanically, the little flag can point in any direction in the xy plane. So photons carry little flags. The flags are their polarization vector. The polarization vector is perpendicular to the motion of the photon. But it's an odd little flag. It has some very peculiar properties. So let's first of all go through some of the simple properties that it has and why it is so odd. First of all, you can send the photon through polarizers. Now, polarizers are really not terribly quantum mechanical necessarily. As I mentioned, I think the previous time, if you send microwaves or radio waves through a grid of wires like so, the photons, or better yet, not better yet, but the radio waves or the microwaves that go through it will come out on the other side polarized. And the easiest way to think about it is to think about it in the language of waves, electric and magnetic fields. The electric field can vibrate vertically and horizontally, but it can only drive current in the vertical direction. Now, a mirror is a system such that when an electromagnetic wave falls on it, an electric conductor, is such that current can flow due to the electric field in any direction, and the flow of that current produces its own wave, and typically what it does is it produces the reflected wave that reflects back off the mirror, and that is why mirrors reflect, because they produce currents in there, and those currents produce the reflected wave. Exactly how that works we don't have to worry about here, but it also works in this grid. The only difference is that the electric current can, the electric current can only oscillate in the vertical direction. And so as far as the vertical direction goes, the grid is a mirror. It reflects waves whose electric field is vertical. As far as the horizontal direction goes, the grid isn't there at all. The electric wave cannot drive currents in the horizontal direction, so it's exactly as if there was no grid there at all, and the photon just goes straight through. So the result is a grid like this produces an electromagnetic wave which is polarized. The official definition of the polarization is it's the direction of the electric field. And so a grid like this will produce a photon or an electromagnetic wave polarized this way. I'll represent that by just drawing my polarizer as having an axis, the axis of polarization, not the axis of the grid lines, but the axis that the electromagnetic wave that goes through it becomes polarized in. All right, so we send through photons one at a time, and the photons come through. If they pass through a polarizer like this, they come out polarized in the x direction. Let's call that polarization, let's just call it x. And never mind that we're doing quantum mechanics for the moment, the photons just come through. If we send it through a second polarizer to make a check that it really was polarized horizontally, if the second polarizer is also polarized horizontally, then the photon will again go through. So we can think of the polarizer as both a preparer of systems. It prepares a photon with a particular polarization, and it can also be thought of as a detector, or better yet, a measuring apparatus that measures the photon polarization. In particular, if the photon was horizontally polarized, it will pass through the horizontal polarizer. On the other hand, if the photon was created vertically polarized, I don't need to put arrows on these things, it's good enough just to put a direction. If the photon is created vertically polarized, and the apparatus is horizontally polarized, then the photon will not go through the apparatus. It may get reflected, or it may just get absorbed, one or the other. But whichever it does, by monitoring whether the photon goes through over here or not, you have measured whether the polarization is vertical or horizontal. All right, now there's nothing terribly non-classical about this. You can easily imagine a classical setup where some kind of device which let through a vertical flag would block a horizontal flag and would admit a vertical flag, and vice versa. There's nothing particularly, and this is entirely deterministic. If you send the photon, if the photon is vertically polarized, it'll pass through. If it's horizontally polarized, it won't pass through. End of story. Nothing out of the ordinary there. The place where the out of the ordinary happens is when we add to this picture the idea of symmetry. No, but you could imagine that there are bullets which have little flags on them. Bullets with little, funny shaped bullets with flags on them like that. And they go through. If they're along the direction of some kind of slits, they get blocked otherwise. Nothing special. So classical particles could easily do this kind of thing. The place where you start to get into trouble thinking classically is, oh, one other thing. Notice that there are also only two possibilities for the photon. It either goes through or it doesn't go through in this setup. Now comes the kicker. The kicker has to do with symmetry. The symmetry is the symmetry of rotation of the xy plane. If it's possible to hold your polarizer vertically, and it's possible to hold it horizontally, then the symmetry of physics, which allows you to rotate things, allows you to construct a polarizer which points at any angle. What happens to a photon which goes through that? It comes out polarized at an angle. Well, you can imagine classical setups. For example, a kind of setup which would allow this particular kind of bullet to go through. The other kind of bullet, which was polarized horizontally, would not go through. Any kind of device that I try to think of like that, I tend to find would also block a bullet that was polarized in some non-vertical or non-horizontal direction. For example, if the polarizer literally consisted of a bunch of a grid like this, which passed things which were vertical, blocked things which are horizontal, they would also block things which were not horizontal. Here's where the kicker is. The kicker is that these non-vertically or non-horizontally polarized photons may or may not go through this polarizer. They may or may not go through with a probability. What's more, there is only two possibilities. The photon doesn't get broken into pieces, some piece of it going through, some piece of it not going through. There are only two possibilities, and that's it. It either goes through or it doesn't go through, even though it has been polarized in some other direction. That's where the peculiarities of quantum mechanics start. That's where you begin to wonder, is the photon really behaving like a particle, like a sensible particle or not? And it gets even weirder and more mysterious when we start to set up a theory of the probabilities for the photons to pass through the respective polarizers. That theory is, of course, quantum mechanics. And it is really quite hard to think of a classical setup which would produce the same kind of probability distributions and how they depend on the orientation of the polarizers. I don't think anybody has ever successfully designed such a thing, at least not in any great generality, that would do the right thing to polarized photons. By design, I mean design a classical apparatus which would do the right thing. So there are only two possibilities. The photon either appears to be polarized up or appears to be polarized horizontally when you detect it. When you detect it with a horizontal polarizer, it either goes through or it doesn't go through. So you would be likely to say there's only two possible states for the photon. On the other hand, there's more than two possible states. There's a continuum of possible states for the photon. You can polarize it in any direction. And so we have a kind of conflict between discreteness and continuity. Continuous direction in which the photon can be polarized, but when we monitor it and we detect it, there are only two possible states, one or the other. And that's the mystery of quantum mechanics. It's a conflict between symmetry on the one hand and discreteness on the other hand. Okay, so we were beginning to set up the theory of polarization. As I said, it is probably the simplest context in which to study quantum mechanics. It doesn't have the full complexity of all of quantum mechanics, but it's the simplest quantum mechanical system. All right, so let's now label the quantum states of the polarization of a photon. I will make this phrase shorter. I will simply say the quantum states of a photon, but I mean its polarization. All right, it can be polarized horizontally. Incidentally, there is no difference between being polarized horizontally to the right or polarized horizontally to the left. That's why I tend to draw double arrows on the polarization. There's no difference between being polarized to the right or polarized to the left. If you think about it for a moment, an electromagnetic wave will oscillate up and down, and so there's no sense in which you can say the polarization is vertical versus, vertically up versus vertically down, and the photon inherits that fact. Polarization, you can think of a polarization vector, but it kind of has two ends. There's no sense in which it points to the right rather than to the left, but there is a sense in which it's pointing horizontal rather than vertical.
So
Oh,
that, that way it's simpler than the spin when half system looked at.
well, they're actually quite isomorphic to each other. They're completely parallel, completely identical mathematics. And the reason for not doing it this time, the spin, is because I did it last time. Right? That's the main reason. Some people find it a little easier to visualize the polarization of a photon. They're identical systems quantum mechanically, and so we don't really need to distinguish them. Well, okay, let's go on. All right, we're going to give that the name X. That's the Ket vector X. It represents a photon polarized horizontally. And another way that we can label it, I'm going to take these arrows off. I get awfully tired of drawing arrows, and they serve no purpose whatever since there's no sense of direction along the arrow. And I'll also label that 1, 0. Another representation of the, oh, incidentally, the vector space of states is clearly two-dimensional since there are only two possibilities for the polarization. Two possibilities for the polarization, X or Y, and we'll label Y 0, 1. All right, so several different representations to label the states of the photon polarization. Yes?
Is that totally arbitrary, 1 and 0? Could be anything else, or?
No, it's not totally arbitrary. We want these vectors to be normalized. Sums of the squares of the components should add up to 1. That's one of the rules about state vectors. That corresponds to the total probability for a state adding up to 1. We want them to be orthogonal to each other. These two vectors are clearly orthogonal. Multiply the top by the top plus the bottom by the bottom. Incidentally, in order to take the inner product, you should complex conjugate one of them, but the complex conjugate of the bottom one is itself. So it's 1 times 0 plus 0 times 1. X, Y equals 0. They're orthogonal. They're normalized. They form a basis. Now, it's not completely...
In some sense, you've chosen your axes so that those will be more.
Yes, I have. Now, I could have... We will see that these vectors are somewhat ambiguous. We're going to calculate the things which really count, and when we calculate what really count, namely probabilities, we'll find out that we can't, for example, distinguish this vector and this vector. The fact that there's something in the first place and nothing in the second place is the important thing, and the other important thing is that the sums of the squares of them add up to, sums of the squares of the two components add up to 1. But this is a convenient basis of the vectors which represent the two states. Okay. We also said that we could define an observable. An observable means the thing that we measure or that we record in our little book. We send a lot of photons through. If a photon goes through the apparatus, we say +1. If it doesn't go through the apparatus, we say -1. Now there's absolutely nothing unique. I could have said 7 and 12, anything I like, just to distinguish the two possibilities. 1 and -1 are a nice pair of numbers that they're easy to remember, and there's no particular significance to choosing 1 and -1. It's easy to remember, has a nice symmetry to it. And so what we'll say is that the X polarization, we'll say, has polarization plus, and the Y polarization has polarization minus. Again, what I mean by that is we send a lot of photons to an X polarizer. If they pass through, each time a photon passes through the X polarizer, we write down a little plus in our notebook. Each time it is reflected or whatever else happens to it, we write down a little minus. And then we can take statistics. We can define the observable quantity in the way that I said and label it or associate it with a quantum mechanical observable. A quantum mechanical observable is an operator. I'll put a little hat on it. If I forget to put a hat on it, as long as it's this big double P here, it means an operator. It's an operator whose eigenvectors are x and y, or 1 and 0, or this one and this one. And it has eigenvalue +1 for x and -1 for y. That's unique. Abstractly, we know how it acts on any vector, because any vector can be linearly expanded in x and y. But here's the statement. This is equal to x, and p on y is equal to -y. The eigenvalues are +1 and -1. And I'm going to label this thing here just to indicate that it's a polarizer, that it represents polarization in the xy plane. I'm going to put a little symbol here that represents the fact that it has to do with the xy plane, as opposed to some rotated direction. Okay, so this is its definition. It's an operator, a linear operator. Associated with every linear operator is a matrix. The matrix associated with P is the matrix 1 minus 1. As simple as it could be. And it's obvious now that when it acts on the vector x, let's let it act on the vector x. The vector x is represented by 1, 0. That matrix times that column vector, 1 times 1 is 1. 0 times 1 and 1 times 0, -1 times 0, 0. So we see that the P observable, when it acts on the x vector, gives x polarization, gives us back the x polarization vector. But when it acts, when it acts on the y polarization vector, it gives minus the y polarization vector. So this is the unique operator which represents the observable polarization in the xy plane. Now in this case, we knew what we wanted, we constructed the vectors, and then we made up an observable, and we concocted it just so it would do what we wanted it to do. In other cases, and I'll give you an example of another case, in other cases, there might be reasons to focus on an observable, on an operator, and ask what its eigenvectors are and what its eigenvalues are. The example that I've already given you was, for example, the momentum. The momentum was described by an operator, -I d by dx. I told you what the operator was, and then we found its eigenvectors and its eigenvalues. So sometimes it's more convenient, not a question more convenient, sometimes we know more about the vectors and the eigenvalues than we do about the mathematical structure of the observable, and sometimes we know it the other way. But either way, observables have eigenvalues and eigenvectors. The eigenvectors are the states in which the observable has a definite value, and that value is the eigenvalue. So we're back to the basic foundations of the subject and the postulates. We have an example of them. Now, what if we polarize at 45 degrees? What if we turn our polarizer through 45 degrees? I know we did this before, but let's do it again. If we rotate our polarizer through 45 degrees, then we encounter a new state of polarization. It's neither x nor y. It clearly has, it's intuitively obvious that it has equal probability when the photon is prepared this way and then goes through the x or y polarizer. It's intuitively obvious that it will have equal probability to go through either the x or the y polarizer, since it's polarized at 45 degrees. Okay. So it makes sense then to identify this polarization, which I'll label that way, as 1 over the square root of 2, that's just there to normalize it, times x plus y. Equal likelihood for the polarization to be up or horizontal if it goes through the polarizer which detects x polarization. We can also represent this in another way. We can represent it as a column vector, 1 over square root of 2, 1 over square root of 2. Equal coefficients in terms of x, or in front of x and in front of y. All right, what about the other orthogonal polarization? The other orthogonal polarization, I won't draw it in here, but it points in the orthogonal direction. That's equal to 1 over square root of 2. And that can be taken to be, now the one thing we know about it, and about the only thing we really know about it, is that it should be orthogonal to this vector. Orthogonal to this vector. Why orthogonal to it? Because it represents a completely distinct, different outcome of an experiment. Namely, the experiment of sending it through the 45-degree polarizer. All right, things which represent different outcomes, different definite outcomes of some experiment should be orthogonal to each other. Well, a simple vector that's orthogonal to this would be x minus y, not x minus x minus y, or 1 over root 2 minus 1 over root 2. Now, it makes no difference whatever if you put the minus sign in front of the x with no minus sign in front of the y, or vice versa. We'll see. It makes no difference. All we need to do is to choose a second vector orthogonal to this one. Let's check that it's orthogonal. The inner product between this vector and this vector is the sums of the x components, the product of the x components, and the product of the y components. So it's 1 over square root of 2 times 1 over square root of 2 minus 1 over square root of 2 times 1 over square root of 2. The inner product is 0. Again, I didn't have to worry about complex conjugating because everything is real. So we can write down equals 0. They're also normalized. The sums of the squares of the coefficients add up to 1. 1 over root 2 squared plus 1 over root 2 squared is 1. So the two vectors are another basis. They're a different and separate basis of states, but they're just as good as the original basis. The original basis was the basis 1, 0 and 0, 1. Here's the second basis. These are also mutually orthogonal and also normalized. Roughly speaking, well, you can see what you can see the point. I don't need to belabor it. What happens if we start with a polarizer, polarized at 45 degrees like that? We send the photon through it. It comes out the other side, and then we send it through a polarizer which is either vertical or horizontal. Let's take the horizontal case. Then the rule of quantum mechanics is, well, let's begin. What is the state of the photon when it comes out of the first polarizer? When it comes out of the first polarizer, here it is. It's this. So when it comes out of the first polarizer, the state of the photon is like that. What is the probability that if we measure the observable associated with the XY polarization, that we get plus? The answer is, again, this goes back to the basic postulates. We take the inner product of the state that we've constructed. We take the inner product of that with the eigenvector of the observable of interest. The observable of interest is now this observable, and its eigenvectors are x and y. So we take the inner product, for example, of this with x, and we square it. That will give us the probability that after having gone through the first polarizer, it also goes through the second polarizer. Okay. That's the probability that after going through the first polarizer, it then goes through the second polarizer. We could also draw this x as just a horizontal line here. What is this? This is the inner product. Let's write them down. The bra vector here can be represented as a row vector, 1, 0. The ket vector is a column vector, 1 over root 2, 1 over root 2. And the inner product between them is just 1 over root 2. 1 times 1 over root 2. The probability is the square of that. So I shouldn't have written equals here. I should have taken this away. This is true now. And the probability is the square of this. Equal 1/2. Okay, so that was intuitively clear in the first place that the probability for the photon to go through the second polarizer would be 1/2, since it was polarized at 45 degrees. Likewise, if we ask what's the probability that it would pass through a vertical polarizer, same answer, slightly different reason. To calculate that, we would put y here, but that's also equal 1 over square root of 2. And so both cases we would get the probability being 1/2. Again, not surprising. Can we construct an observable which represents the photon polarization not in the vertical and horizontal direction, but in the 45-degree directions? Let's see if we can do that. Let's invent the polarization now, and let's call it this. Let's call it that way. It has the property that when it acts on, I wish I had names for these two vectors. Anybody think of names for the two vectors, the slanty vectors? I want a name for both of them. I mean, for each of them. Slash and backslash, good. Okay, so the observable associated with slash and backslash, I will define to be +1 on slash, and I'll define it to be -1 on backslash. What's the observable? Can we find it? Yeah, it's not hard. I'll just tell you what the answer is, and then we'll check it. The matrix that's associated with it is rather simple. It's 1, 1, 0, 0. Let's check that that acts on slash to give back slash and acts on backslash to give backslash. All right, slash is just 1 over square root of 2 times 1, 1. Where is it? The 1 over square root of 2 here doesn't, here it is. Here's slash. It's 1 over square root of 2 times 1, 1. If a thing is an eigenvector, so is any multiple of it. So we don't need to keep the square root of 2 in checking whether it's an eigenvector. We do need to keep the square root of 2 if we want to normalize it. But if all we want to do is check for eigenvectorness, we need not keep that square root of 2 in the problem. All right, so what does this give? It gives 0 times 1 plus 1 times 1. 1. 1 times 1 plus 0 times 1 is 1. So that is, in fact, what the observable is supposed to do on slash. It gives backslash. Let's now try it on backslash. 0, 1, 1, 0 on 1 minus 1. What does that give? 0 times 1 plus 1 times minus 1. That gives minus 1. 1 times 1 is 1. Notice that the right-hand side is the negative of backslash. So in fact, the observable on backslash does give minus backslash. This is equal to minus 1 minus 1. Okay, so we've actually succeeded in constructing the observable associated with 45-degree polarization.
A question.
Yes.
Would it be accurate to say then that if you define the states, then you restrict what's observable?
Yeah, if you have a particular state, you may ask, you can't ask what's observable. Anything is observable if it's unobservable, but you can ask what is definite. Given a particular state, let's say slash, are there any quantities which when you measure them will give you definite deterministic answers? Well, if you measure the original observable, you won't get definite answers. You'll get a half a probability one way, a half a probability the other way, if you start with slash. On the other hand, if you measure this observable, the polarization at the 45-degree angle, then you will get definite answers for slash and backslash. This corresponds, of course, to sending slash and backslash through the slashed or backslashed polarizers. So it's not right to say that, that if you're given a state, it determines what's observable. No, it determines what's definite. It determines what's predictable about measurements on that state. Another example is if you're given a wave function, any wave function, you can measure the position of the electron and the momentum of the electron. If you just take a random wave function, any old wave function, you'll have a statistical probability for different momenta and different positions. Neither will be definite. But if you take a delta function, which is a very particular state, delta function of position, then you measure the position, it'll be definite. It'll be right where that delta function says it should be. If you take a plane wave, a cosine, not a cosine or a sine, but an e to the I kx, and you measure the momentum, then the momentum will be definite. So given a state, it restricts the class of things which are deterministic. It's not the right word. What's the right word? Definite, I suppose, certain. Okay, so this is the object, the mathematical representation of the object which is definite for slash and backslash states. It happens that I defined it so that it's positive, so the eigenvalue is +1 for slash and -1 for backslash. I could have defined it the other way, then I would have put a minus sign in front of it, but that's not important. Okay. Well, so far we have polarizers which are oriented that way, and polarizers which are oriented that way. We can, of course, orient the polarizers in any direction in the xy plane. So let's discuss that possibility now. Arbitrary angle. Let's have a polarizer now which is polarized in the arbitrary angle theta. Theta relative to the horizontal. Then there's another polarizer which is orthogonal to this, which is polarized in the perpendicular direction, polarized this way. We don't need to invent a new label for this. This is just the polarizer whose angle is theta plus pi over 2. Pi over 2 is 90 degrees. If you take theta and you add 90 degrees to it, it becomes perpendicular. So we can label the two states theta and theta plus pi over 2. They represent the two orthogonal combinations, the two mutually exclusive combinations if you send a photon through. Any photon which goes through a theta polarizer will pass through a second theta polarizer, but it will get blocked by a theta plus pi over 2 polarizer. That's a mouthful. The two vectors, the two eigenvectors that go with it, if you pass it through the theta polarizer, you get out the state theta. I'm going to tell you what it is, how it's related to the other states. in a more or less obvious way. And this one will be called theta plus pi over 2. These two should be orthogonal to each other, but they're not likely to be orthogonal to the previous states. In fact, if this goes to a vertical polarizer, it won't get blocked, or it may get blocked, but it may not get blocked. So we don't expect this to be orthogonal to the vertical polarization or the horizontal polarization, or for that matter, the 45-degree polarization. It's not going, but they should be perpendicular to each other. They should be orthogonal to each other. Okay, so let me tell you what this is. Now, the justification for this is ultimately experimental, but it makes sense. It makes intuitive sense. We're rotating the horizontal polarization by an angle theta. We started with that polarization in the horizontal, and now we rotate it by angle theta. It shouldn't be too surprising that the answer is cosine theta times the x polarization plus sine theta times the y polarization. Or equivalently, cosine theta, sine theta. In fact, cosine theta and sine theta are simply the components of a vector, a unit vector, along the theta direction. So that's not too surprising. How about this one? This one had better be exactly the same, except wherever you see theta here, you should stick in theta plus pi over 2. So this should be cosine of theta plus pi over 2. But what's the cosine of theta plus pi over 2? Well, not quite. Close. Minus the sine of theta. Cosine of theta plus pi over 2 is minus the sine of theta. Let's just check why that's so. All right. Here's the sine of theta. Here's the cosine of theta. Now, here's theta plus pi over 2. Okay? Notice that the cosine of theta plus pi over 2, that's the x projection here. The cosine is the x projection. The cosine here is negative, but the sine is positive. So the cosine of theta plus pi over 2 is minus the sine of theta. Sine minus sine theta, x, plus the sine of theta plus pi over 2 times y. But what's the sine of theta plus pi over 2? That's cosine theta. Okay, now we can represent this bottom case here by minus sine cosine. Okay, this one represents a photon polarized along theta, and this one represents a photon polarized in the orthogonal direction. Are these orthogonal basis vectors? Well, first of all, are they normalized to unity? In other words, is the length of them equal to unity? Well, that's just cosine squared plus sine squared equals 1. Cosine squared plus sine squared equals 1, so they're normalized, both of them. Sine squared plus cosine squared is equal to 1. Again, no complex numbers in these vectors here, so we don't have to worry about complex conjugation. Next, are they orthogonal? Let's check that. Cosine theta times minus sine theta plus sine theta times cosine theta. Obviously, they are orthogonal. Cosine times minus sine plus sine times cosine adds up to 0. So yes, they also happen to be orthogonal to each other. Theta plus pi over 2 equals 0. And we've got yet another basis. We've got yet another basis of vectors for our space of states. It represents a physically different kind of experiment, a similar kind of experiment, but different in that the direction of the polarizers are now in an arbitrary direction, theta. Okay, now we can ask the question. Supposing we construct one of these theta photons, a photon polarized along the theta axis, what's the probability that if we send it through an X polarizer that it will pass through? So let's do that experiment. I mean, this is exactly the kind of question that quantum mechanics is set up to answer. We have our theta polarizer over here. We send our photon, I'm going to make a red photon this time. We send our photon through. Of course, the photon may not go through. The photon may have been polarized in some wrong direction. But if it gets through, it is then a theta polarized photon. It's now a theta polarized photon, and we now send it through a second polarizer, which I'm going to take to be an X polarizer. What's the probability that it goes through? Question mark. Does it or doesn't it? And if it does or doesn't, what's the probability? This is the kind of question now that classical mechanics, it would make no sense in classical mechanics. And classical mechanics is deterministic. It either goes through or it doesn't go through. Okay, so let's figure it out. All we have to do is take the inner product between theta, that's our starting vector here in the middle, and X. The square of this is the probability. Okay, so what is this? This is, we can work it out using the column vectors and row vectors. The X is the row vector 0, 1, or 1, 0, excuse me. And theta is the column vector cosine theta, sine theta. And that inner product is just cosine theta. 1 times cosine theta plus 0 times sine theta. That inner product is just cosine of theta. Incidentally, notice that it doesn't matter whether you take either way, x theta or theta x. The reason is that although in general these objects are complex and different than each other, they're complex conjugates of each other. When you square them or when multiplied by their complex conjugate, it doesn't matter which order you put them in. Okay, but in this case especially where everything's real, it certainly doesn't matter. And then the probability over here, the question, the probability question, this is not the observable, this is the probability. This is the probability that if the photon was polarized in the theta direction, that it passes through the X polarizer. Okay? That probability is the square of this inner product. In other words, it's cosine squared theta. Notice it's cosine squared theta, not cosine of theta. What's the probability that it passes through the Y polarizer? Let's send it through the Y polarizer. Through the Y polarizer, that's going to be very similar, except we're going to put Y here, and that's 0, 1. This gives us sine theta. That's going to give us sine squared theta. What's the total probability that it will either pass through the, well, the total probability, if we add up the probabilities that it's X polarized or Y polarized, it's either X polarized or Y polarized, here's the probability that it's, squared. It's either X polarized or Y polarized with probability cosine squared theta and sine squared theta. The total probability adds up to 1. Okay, so here's a slightly more intricate example of a quantum mechanical problem where we send something through at an arbitrary angle and then measure its polarization along the vertical or horizontal direction. We can go further. We could send it through a polarizer in the 45-degree angle here. We have enough information to figure out the probabilities that it'll go through 45 pi over 2, the pi over 2 polarizer. But why work that out? Let's just send it through an arbitrary angle, the first one, and a second arbitrary angle, the second one. I'm going to call those angles, I hate using primes, so I'm going to call them alpha and beta. Alpha and beta are also good Greek letters. When it passes through the first polarizer, it comes out alpha polarized. And then we want to know what's the probability it will pass through the beta polarizer. Let's check that and see if we can get a general formula which will serve for all possible polarizers. What's the answer going to depend on? Is it going to depend on alpha times beta, alpha plus beta? Alpha minus beta. The relative, the angular distance between them. It better, otherwise we're doing something wrong. Right, okay, so let's check it out. All right, here's where I either shine or don't shine. Okay, so let's take the alpha, let's take the inner product of the alpha vector with the beta vector. The alpha vector, before we do so, let me do a bit of review of trigonometry, a review of some trigonometric formulas that we'll use. Keep in mind what problem we want to solve. Two polarizers at arbitrary angles, but we need a bit of trigonometry. So let me just write down the trigonometric formulas that we need. Cosine alpha plus beta equals, anybody know? Cosine alpha, cosine beta minus sine alpha, sine beta. Now, while we're at it, we're going to wind up also wanting cosine of alpha minus beta. And to get the cosine of alpha minus beta, we just change the sign of beta in this formula. Changing the sign of beta does nothing to cosine beta, but it changes the sign of sine. It changes the sign of sine. It changes the sign with a G of sine without a G. Got it? Okay. So that gives us cosine alpha cosine beta plus sine alpha sine beta. Notice we don't change sine alpha. We haven't done anything to alpha. We've only done something to beta. We will also need sine of alpha plus beta. And that is equal to sine alpha cosine beta plus sine beta cosine alpha. And while we're at it, let's also do sine of alpha minus beta. Again, all I've done is change beta. It doesn't change the cosine of beta, but it does change the sine of beta. So this becomes sine alpha cosine beta minus sine beta cosine alpha. There's a nice check we can do. What if alpha equals beta? If alpha equals beta, we have cosine of 0. Cosine of 0 is what? 1. All right. On the right-hand side, we would have cosine of alpha squared. Alpha is equal to beta. Cosine of alpha squared plus sine of alpha squared. That's 1. Cosine squared plus sine squared. So that works. How about sine of alpha minus beta? What should that be? If alpha equals beta. That should be 0. So if alpha equals beta, these two will cancel each other. Okay, one more. Cosine of 2 alpha. That's easy. We just read it off from here. That's cosine squared alpha minus sine squared alpha. And sine of 2 alpha, we read from here. That's just twice sine cosine. All right, here's our trigonometric table of formulas. And we'll use them. Okay, so we pass through the first polarizer. It's the alpha polarizer. And what comes out is the alpha ket, alpha, which is equal to cosine alpha. Let's just write it this way. Cosine alpha sine alpha. Just using this formula, replacing theta by alpha. Okay. So we pass through the alpha polarizer. But now we're testing for beta polarization. The beta ket is, of course, cosine beta sine beta. Or I really want the bra vector. So the bra vector is beta is equal to the rho of cosine beta sine beta. We just turn it and make a row vector out of it. Now what's the inner product? The inner product of alpha and beta, beta alpha, is cosine alpha times cosine beta plus sine alpha times sine beta. And lo and behold, I hope, that's the top formula, which is, no, it's the second one, which is cosine of alpha minus beta. Now that's, of course, not the probability. That's the thing that we square to get the probability. So the probability is just cosine squared of alpha minus beta. How could you be absolutely sure that this wasn't the probability, even if you didn't know any quantum mechanics? Yeah, because it can be negative. Right. All right. Here's our formula. Indeed, it only depends on the difference between the angles. But let's look at it a little more carefully. First of all, what happens if beta is very, very close to alpha? In fact, what happens if beta is equal to alpha? If beta is equal to alpha, we get cosine squared of 0, which is 1. So that simply says that if we polarize along the alpha direction and then we send it through a polarizer very, very close to the alpha direction, it has a very high probability of getting through, almost equal to 1. Cosine alpha minus beta is almost equal to 1 if alpha is close to beta. And as beta is rotated away from alpha, this gets smaller. When they're 90 degrees apart from each other, then the cosine of 90 degrees is 0, and there's no probability to go through. So the formula makes some sense. Formula looks good. But keep in mind, we're doing something interesting and unusual. There are only two possible outcomes to the beta experiment over here. There are only two possible things that can come out of the alpha polarizer over here. And yet, we're finding answers, but answers which are probabilistic. Answers which are probabilistic and equal to the square of quantum mechanical amplitudes. These inner products are called amplitudes. Their squares are probabilities. All right, let's see. Should we take let's take a few minutes break. And what we haven't done yet is found the observable for a general polarization. The observable for a general polarization we'll do next. All right, so two people asked me an interesting question, and it sort of does point out one of the somewhat mildly, I don't know, it depends on who. I've known it for so long that to me it's mildly freaky, but here's the issue. Supposing you send a photon through a polarizer which is polarized, let's say, in the theta direction Not horizontally, definitely not horizontally, but in some arbitrary direction. And then you're going to send it through a second polarizer, or third. I'm going to call this the third polarizer up here, far away. And it's polarized in the orthogonal direction, theta plus pi over 2. Of course, the first photon may or may not get through, but let's suppose it gets through. It's polarized in the theta direction, and it will not make it through the theta plus pi over 2 polarizer. But supposing we put in between a polarizer, let's say, in the vertical direction, or let's make it the horizontal direction, for no good reason other than then, does it get through or doesn't it get through? The answer is it gets through with a probability. The probability we can calculate. Let's calculate the probability. Well, let's work it out. I don't know. I haven't worked it out. The first question is, what's the probability that it gets through the horizontal polarizer? All right? I think we have a formula for the horizontal polarizer that corresponds to beta equals 0. And the answer was just cosine squared theta. There's a probability cosine squared theta that the photon makes it through the first polarizer here. Cosine squared theta. But now, when it makes it through the first polarizer, it is now polarized in the horizontal direction. It is no longer polarized in the theta direction. If it makes it through, it's polarized in the horizontal direction. So what's the probability that it goes through the third polarizer? It is cosine squared of, now we have to take the angle over here minus the angle over here. That's 0 minus pi plus theta over 2. Cosine of, so it's cosine of theta plus pi over 2, which is what? Sine squared theta. I think I did that right. Not added, but multiplied. The probability that it goes through the first one is cosine squared theta. And then if it does, it's horizontally polarized. If it's horizontally polarized, then the probability that it goes through the second polarizer is sine squared theta, which is the same as cosine squared of theta plus pi over 2. What's that? Well, say it again now. This is less than 1. Right, there is less than 1, so it passes through this polarizer with a probability less than 1. Each time you cut down the probability, so the probability, if you do a lot of polarizers like this, of course, will go down with the number of polarizers. But by putting this one in, you take a photon which was polarized in the theta direction and could not go through the second one, and now allow it. So this is one of the, whether you find this anti-intuitive or not is
It gets an assist.
right.
If you actually do that, you'll get, based on the angle in between, you actually get a different color. If you start off with...
That may be, but I don't know why.
And no, it does happen.
I don't know why.
I've seen it, so I
No,
always...
no, it may be so. I don't know why it's true, though. Well, polarizers...
You wouldn't change the energy of the photon.
No.
Yeah, well, yeah, but do keep in mind that polarizers have different efficiencies for different colors, so it might, I would have to think about it. But,
It's also used as a stress test for glass.
yeah, that's true. I've seen them do things like that. So I don't know offhand. I would have to think about why that's true. But it probably has to do with the fact that the efficiency for polarization is frequency dependent.
It's optical by the time. Yeah.
I think the high frequency light goes through because the slits are too wide that for a wavelength.
Perhaps let me think about it. It's completely something I didn't even know, so I need to dwell on it a little bit. Okay, good. It's an interesting fact if it's true. But this is kind of an interesting quantum mechanical fact that it's an interference effect. It's a funny kind of interference effect that something you would have thought that whatever the probability to go through the second polarizer was, you would have diminished it by putting something in the way, huh? By putting something else in the way which cuts down the probability. You would have thought that you diminish the probability. Well, as you can see, it's not always true. So this is one of these interference phenomena. Okay, let's see if we can find the observable. Now, we're not learning very much by figuring out the observables in these cases. I just want to show you that they exist, they make sense, their eigenvalues and eigenvectors are correct. Are correct. There are lots of other cases where we know much more about the observables than we do about anything else, and then we work in the opposite direction. But okay, we're interested now in the observable representing polarization in the theta direction. In other words, by definition, this one's a little bit thicker. By definition, P theta acting on theta gives us plus theta, and P theta acting on theta plus pi over 2 gives us minus theta plus pi over 2. In other words, both of these vectors, both of these polarization states, theta plus pi over 2, they're both eigenvectors of the observable polarization, but eigenvectors with opposite eigenvalue. Let's see if we can, I'm not going to see if we can find it. I'm going to write down the answer and then show you that it works. It took me about 15, well, less than 15 minutes, 10 minutes to work it out. And all I did was solve, I simply wrote these as algebraic equations and solved the algebraic equations component-wise. It was not very illuminating, but it's mildly illuminating to see the answer and then check it. So the answer is, where is the answer? Here it is. P theta is equal to cosine minus cosine sine sine. But cosine and sine of what? Anybody want to guess? 2 theta. Let's check that when this object acts on theta, it gives back theta. So let me erase the left side of the equation here because it's not going to be an equation anymore. Let's multiply it by theta. Now, let me first rewrite this. Cosine of 2 theta. Cosine of 2 theta is cosine squared theta minus sine squared theta. That's in the upper left. Here we have twice cosine theta sine theta. Do anybody mind if instead of writing cosine theta and sine theta, I'm just going to write C and S? C and S for cosine and sine theta. There will be no confusion since there's only one angle here. So this is C squared minus S squared. This is twice SC. This is twice SC. And this is S squared minus C squared. And we want to apply this now to theta. Well, what is theta? Theta is CS. Look up on the upper right corner, CS. Okay, let's just work it out. Okay, so we have to multiply c squared minus s squared by c. So in the upper place we have c squared c minus s squared c, that's this times this, plus twice sc times s, plus twice sc times s. What about in the bottom? In the bottom we have twice sc times c, twice sc times c, twice s, I leave it that way, twice sc times c, plus s squared s minus c squared s. Okay. Don't ask me why I wrote it in this clumsy way. I don't know why. We have twice s squared c over here. This is twice s squared c over here. But we have minus s squared c over here. So the plus 2 and the minus 1 conspire to change this to a plus sign, and we get rid of this. Now we have c squared plus s squared times c. C is a common factor in both of them. So let's take c outside. And now what is c squared plus s squared? 1. So this is just c. That's good because we want to get, remember what we're trying to get, that p theta on theta just gives us back theta. Okay, now let's look at the lower piece here. Twice SCC. Here's minus CCS. So the 2 again conspires with the minus sign, turns it into a plus sign, and now we have s squared s plus c squared s, and that's just s. So we check explicitly that p theta on theta gives us back theta, and I'll leave it to you to check that p theta on this guy here gives minus itself back again. So these two vectors, where are they? CS and minus SC are the eigenvectors of the observable. The observable is Hermitian. How do you tell that it's Hermitian? Remember what Hermitian means. Hermitian means that if you reflect about the diagonal and complex conjugate, you get back to the same thing. For real matrices, we're going to talk more about Hermitian, but for real matrices, Hermitian just means symmetric. This is a Hermitian matrix. Its eigenvectors and eigenvalues satisfy certain requirements. The eigenvectors are orthogonal. The eigenvalues are real. This is the observable that goes with the polarization along the angle theta. What happens, incidentally, interesting question. Supposing I took this, here's the observable for angle theta. What is the observable for minus theta? What happens to minus theta, to the observable minus theta? That's not really what I want to do, is it? I don't think that's what I actually want to do. No, that's not what I wanted to do. Sorry, that's, what I wanted to do was to look at the observable for theta plus pi over 2, for theta plus pi over 2. What happens to observable for theta plus pi over 2? What should happen to it? If this is theta. What's the cosine of theta of twice theta? Okay. Here's theta. Here's theta plus pi over 2. And where is twice that angle? Minus cosine 2 theta, right? So if we do that transformation, if we rotate by 90 degrees, this becomes minus cosine 2 theta. This one will become plus cosine 2 theta. And what about sine of twice theta plus pi over 2? Also just changes sign, right? So this becomes minus. In other words, what's happened, by focusing on the observable rotated by 90 degrees, it's just changed sign. Well, that makes a lot of sense, because all it's done is interchange the positive eigenvalue with the negative eigenvalue. It's just interchange the positive eigenvalue with a negative eigenvalue. The observable for theta has eigenvalues +1 and -1 for the two states. The observable for the rotated 90 degrees just interchanges the plus sign and the minus sign. That's all I wanted to say, that it interchanges the plus sign and the minus sign. Okay, so that also makes sense. Okay, we've left out of the story an important ingredient, another kind of polarization. That there is another kind of polarization must be so, because we haven't introduced any imaginary numbers yet. Remember, quantum mechanics is all about complex numbers. And there's nothing to prevent us from introducing state vectors with complex numbers in them. For example, here's a state vector with a complex number in it, 1i. Is that normalized? No, it's not normalized. Remember what we have to do. We have to multiply each one by its complex conjugate and add them to find the normalization. 1 squared is 1. I squared, I times minus I is also 1. We need a 1 over square root of 2 here. This is a perfectly good normalized state vector in quantum mechanics. We may not know what it is yet, and in fact, I'm eventually going to tell you what it is, but it has to be there. It has to be some kind of new state vector. It can also be written as 1 over square root of 2x plus I over square root of 2y. It's something that doesn't have an obvious interpretation in terms of these angles. Is there a vector which is orthogonal to it? Of course, there must be another vector which is orthogonal to it. The orthogonal one is 1 over square root of 2 times 1 minus I. Let's check that these two are orthogonal to each other. Well, 1 times 1 is 1. I times minus I is 1. If I add them up, I get 2. That's no good. No, but something's wrong with that. I forgot the complex conjugate. I forgot the complex conjugate. If I want to see whether these two are orthogonal, one of them has to be a bra vector. Let's take this one to be a bra vector. So that means it corresponds to the row vector 1 over square root of 2, 1 plus I. Not 1 plus I, but 1 and I. Not minus I, but I. And that's because we have to complex conjugate in the bra vectors. All right, let's take the inner product of this with 1i with another square root of 2. That'll just get rid of the square root of 2 here and put a 1/2 there. But now we can see this is 1 times 1 plus I times I, and that's 0. Okay. So these two vectors are indeed orthogonal. There must be some observable which distinguishes them. I'm going to leave it to you as a homework problem to find the observable with the following property. I'll give it to you next time, but I'm going to leave it, assign it as a homework problem for fun. I'm not going to collect it, so but and try out your. This one I will call that. This one I will call that. And guess what they are? They are circular polarization. Light can also be circularly polarized. Let me tell you what circularly polarized light means from the wave point of view. From the wave point of view, it clearly means that there is both X and Y polarization mixed in. X and Y polarization are both mixed in here. In fact, if I were to calculate, and I will in a moment, if I were to calculate the probability that it passes through an X polarizer, it'll be 1/2. A Y polarizer, it'll also be 1/2. In fact, we'll see that it passes through probability 1/2 through any one of the theta polarizers. Right? But so it's got both X and Y mixed into it, as we can see. What was I going to say about it? Yeah. So from the point of view of wave theory, it must have the electric field is both in the X and Y direction. In fact, it has more or less, it has equal probability for being in the X and Y direction. The magnitude of 1 and the magnitude of I is the same. So it looks like somehow it's a state with, let's think about now the electric field going into the blackboard. It looks like it has an electric field in the X direction and an electric field in the Y direction. You would think that adds up to an electric field like that, and that it ought to just be a polarization in the 45-degree direction. But that's not right. That's not what a circularly polarized light ray is. What a circularly polarized light ray, let's think about a vertically polarized light wave. That has an electric field which is something like, for example, cosine of z, it's moving down the z-axis, minus ct. This is a wave moving, c is the speed of light. This is a wave moving down the z-axis with the speed of light, and this could be the y polarization, or this could be the y component of an electromagnetic wave moving down the z-axis. The x component, if I wrote that that was also equal to cosine of z minus ct, that would correspond to a plane polarized light ray at 45 degrees. In other words, it would just say that the component of the electric field in the 45-degree axis was cosine, or square root of 2 times cosine of z plus ct, minus ct. But we put them out of phase. We put them out of phase. What that means, now these are the electric fields, no magnetic field. I have not mixed in the magnetic field at all. What this says is if we look, here's the z-axis down here. Here's x. The electric field might be a cosine and look like this. Whereas the other component of the electric field, the y component, is a sine. So where the x component is maximum, the y component is 0, and so on. I don't know if I can draw this. I can never do this. I can never get them out. The thing to do is to draw them in phase and then shift them. Now, take the red one and shift it by 90 degrees. I can never do that. 90 degrees is halfway, and I'm not good at halfway things. Just take the red one and shift it by 90 degrees so that where the y component of the electric field is maximum, the x component is minimum. If you stand at a point, let's say the point z equals 0, stand at the point z equals 0, and look at the x and y component of the electric field. What does it do? it rotates around in a circle. These are the equations for an electric field. Here's the electric field. It has an x component, it has a y component. When the x component is maximum, the y component is minimum, and vice versa. This is an electric field which is just rotating around with a uniform angular motion. That's called a circularly polarized wave. It's a perfectly good wave. It's just a wave whose x and y component are out of phase with respect to each other. It's another solution of Maxwell's equations. Incidentally, the magnetic fields are the same as the electric fields except rotated by 90 degrees. So you could write something similar for the magnetic fields. There are two possibilities. Ey equals cosine, Ex equals sine, and Ey equals cosine, Ex equals minus sine. One of them rotates around in one direction, the other one rotates around in the other direction. Those are circularly polarized light waves. And the individual photons of a circularly polarized light wave are called circularly polarized photons. I've labeled them this way, and this is the state vectors that describe them. Left polarization and right polarization. I might have left and right mixed up. It's not very important for us right now.
What kind of device does that?
A circular polarizer. How do you make a circular polarizer? Anybody know? Yeah. Next time I'll describe how you make a circular polarizer. A quarter wave plate is the right answer, but it is what gets the x and y components out of phase. But there are two new kinds of photons. Of course, they're not really independent kinds of photons. They are new, circularly polarized photons. But what happens if I send a let's answer the following question now. What happens if I send a circularly polarized photon through a theta polarizer? Okay. What happens if I send a circularly polarized photon through a theta polarizer? Well, to answer that, in other words, what's the probability that it goes through? Again, we take the inner product of the circular polarized photon, here it is, with the theta polarized photon, and we square it. I won't square it yet. I'll square it after we calculate it. So let's see. The circularly polarized photon has 1 over square root of 2 and I over square root of 2 for its ket vector. And the theta polarized one has, what is it, cosine theta, sine theta? Did I get that right? Good. Okay, so what's the answer? Let's see. We get 1 over square root of 2. The inner product then is 1 over root 2 cosine theta plus I over square root of 2 sine theta. That's the inner product, or that's the amplitude, the quantum mechanical amplitude. Now we want to calculate the probability. To calculate the probability, we have to multiply this by its complex conjugate. So let's do that up here. This times its complex conjugate is cosine. Let's just call it C. C over square root of 2, well, 1 over square root of 2 times C plus IS, and then another 1 over square root of 2 for, we're going to see, yeah, we're multiplying this by its complex conjugate. So another 1 over square root of 2 times C minus IS gives us 1/2 C squared plus S squared. I times minus I is plus, so it's C squared plus S squared, which is just 1/2. In other words, as you might have expected, for a circularly polarized photon, there's a probability 1/2 that it will go through any linearly polarized. You cannot tell what direction your polarizer is polarized in by the fact that the circular polarization goes through with a probability of 1/2. Whatever the direction of the linear polarized polarizer is, the circular polarized photon will go through with probability 1/2. Okay. You can also say the opposite is also true. A linearly polarized photon has a probability 1/2 to go through the quarter wave plate, which makes circular polarization. But we'll come to that next time. Okay, so this is the basic setup of circular polarization. Of course, once you realize that complex numbers are allowed, then you can put in any complex numbers here. Any pair of complex numbers. It will be any pair such that the sums of the squares come out to be 1. And those define a wider class of polarizations, which are elliptically polarized photons. Elliptically polarized photons are circularly polarized when one of these is real and one of them is imaginary. If both of them are almost real, one of them is real and one of them is close to being real, then it's an elliptical polarization, which is almost a plane polarized photon. Well, I think we'll do a little more with elliptical polarized photons next time if I get a chance. But and don't ask me how you make a polarizer that polarizes elliptical photons. Well, actually, you can ask me next time. I will have an answer for you. I just realized I know how to do it. Good. All right, we're essentially finished with the idea of polarization, photon polarization for the time being. We may come back to it as an example. But first of all, one thing which is obvious is we've defined a whole bunch. Oh, I have not defined for you, I'll do it next time, the observable that goes with circular polarization. It's got some imaginary numbers in it.
We'll know that by then.
You should know that. Yeah, oh, that's right. Was that the homework? That's the homework, yeah. Good, all right, so that's the homework. Find the observable that goes with the circular polarization. But you're going to find, if you find them all, that for any two different polarizations, circular, linear, or anything else, the polarization observables don't commute with each other. That's more or less obvious because they certainly don't ever have common eigenvectors. The eigenvectors of this polarization are 1, 0. The eigenvectors of this polarization are equal mixtures of the x and y. And the circular polarizations have i's in them. They have no common eigenvectors for different polarizations. The implication of that is that the polarization observables do not commute for different directions or type of polarization. The implication of that is, for example, that you cannot measure simultaneously the x polarization. Can you measure simultaneously the x polarization and the y polarization? Yes. X and y, yes. If the x polarization is plus, then the y polarization is certainly minus. They're trivial. They're simply related to each other in such a simple way. And in fact, the x polarization and the y polarization are just negatives of each other. But how about the x polarization and the 45 polarization? No. Those you cannot measure simultaneously, the x polarization and the 45 and the slash polarization. You cannot simultaneously measure the x polarization and the circular polarization because the observables don't commute. And the observables for a theta and for theta plus pi over 2 do commute. They're just the negatives of each other. That's what I showed you a few minutes ago, that p theta is just equal to minus p theta plus pi over 2. That's just interchanging the positive and negative eigenvalues. a thing certainly commutes with its negative. So the polarization for theta and for theta plus pi over 2 can be simultaneously measured. In fact, when you measure one, you automatically know the other. It's just the negative of it. But none of these commute if the angles are genuinely different. So those are examples of incompatible variables. And it just says that you can't have a polarizer which polarizes both in the x direction and the theta direction. It's something more or less obvious. Okay, I want to come to one thing that we have not discussed, the idea of expectation value, which really should just be called average value. Expectation value is a poor choice of terminology. Let me explain why right now. Supposing I have a wave function for a particle that looks like this.
But it's what you want if you're a gambler.
Well, I don't know. Not in this case, I don't think. All right, there's a wave function which is nice and symmetric. It has a lump over here and a lump over here. This could be x, x0 over here. What's the average value of x?
That looks good.
0. And let's suppose these have tails over here, and actually goes right to 0 here. What's the least likely answer that you could get?
Well, you'll never get the average.
You'll never get the average. So the last thing you expect is the expectation value. It should not be called the expectation value. Even worse, Murray-Gell-Mann insists on calling it the expected value. It is not the expected value. It's the average value that we're defining, that I'm going to define now. So let me define for you the average value by first writing down a mathematical expression for it and then showing you that it really is the average value. Suppose you have some observable k, any observable whatever, Hermitian operator k. And I have some state value. It could be the position operator, it could be the momentum operator, it could be one of our polarization operators. The only thing about it is that it's Hermitian and it corresponds to some observable. It has a collection of eigenvectors and eigenvalues, lambda n and n. This is the observable. Here are its eigenvalues. Here are its eigenvectors. K acting on the eigenvector n gives lambda n times n. All right, that's the definition. Now take any state, whatever. I'll call it psi. Operate with k. K is an operator. It hits any vector and creates a new vector, and then take its inner product with psi itself again. In other words, it's a sandwich where the bread is the bra vector and ket vector psi, and the bologna in the middle is the observable k.
No star.
Star?
Well,
No, no star.
did the bra thing.
No, k is a Hermitian thing. Oh, yeah, the bra means that it's complex conjugated. It effectively means it's complex conjugated. Whenever you see a bra, it always implies complex conjugation. Just another symbol for complex conjugation. All right, let's calculate this. Let's calculate it by inserting complete sets of states. Remember that these n vectors here are a complete orthonormal family, a basis of vectors. And let me just remind you of the basic rule that if I make the dyad nn and sum over n, that's just equal to the identity operator and can be stuck into any expression for free without changing it. Since n is a summation index, I could also call it m. It would still be the identity operator. It doesn't matter what I call this, it's a summation index. Okay, let's put such a basis of vectors in here. Psi k hat, and now right over here, n psi summed over n. I have not changed it. This is equal. This is equal to this. But now, what does k do when it hits n? K on n equals lambda n on n. So we can rewrite this as sum on n psi n psi lambda n. What I've done is I've said that k, when it hits n, just multiplies it by the number lambda n. Now n is still inside the sum. Okay, let's erase this. Everybody see what I did? I stuck the complete basis n between k and psi. Then I said that k, when it hits n, just multiplies by lambda n. Now what is this psi inner product with n times n inner product with psi? This is psi n times its complex conjugate times lambda n. And what is psi n times its complex conjugate? It's a probability. The inner product of a state vector with a basis vector representing an observable k is the probability that the system has eigenvalue lambda n. So what this is it's the sum on n of the probability that if you were to measure k, you would get the nth eigenvalue times the nth eigenvalue. For example, if I plot lambda n this way, these are the lambdas. Here's lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. And each one has a probability. Here's the probabilities. Just what do you get if you add up all the probabilities times the eigenvalue? You get the average of lambda. In other words, it's the probability times the thing which you're measuring summed over all the is this obvious to everybody? That if you sum over all the possible values that you can get for a measurement, you sum over all the possible values you get for the measurement with the value for the measurement that you get times the probability that you get that value, that is called the average of lambda. Or you could say that it's the average of k, of the observable k. Better yet, the quantum mechanical notation is just k, representing this thing over here. This is the symbol that's often used for the average of a quantity, just bracket in between, without particularly writing down the vector here. It's just a notation, represents the average. And you can see that what it is just a sandwich of the observable evaluated between the bra vector and the ket vector representing the state of the system. This is why it's often useful to actually have these observables. If you're interested in calculating the average value of a measurement, then if you know the vector that you've prepared, in other words, if you know what you've prepared, psi, and you know the observable, you just sandwich it in this way. Okay? Let's do an example. I'm tired, so I'm going to do the very simplest example. My observable is just going to be 1 minus 1, 0, 0. This is the observable polarization in the xy plane. And now let's take something, the vector theta. In other words, a linear polarization polarized in the theta direction. Okay? What is the average value of this observable? Well, we take theta, we put p, and we take theta again. make a sandwich. Okay. In terms of matrices, that's 1, 0, 0, 1. The ket vector over here is cosine theta, sine theta. And the bra vector is just the row vector, also cosine theta, sine theta. What do I get when this is -1, excuse me. Okay, just take 2 minutes to work it out. Multiplying the matrix by the vector, what does that do? It just changes the sign of the bottom entry. So it just gives you cosine theta, sine theta, times cosine theta minus sine theta. That inner product is cosine squared theta minus sine squared theta. Which is also something else. Cosine 2 theta. All right, so we found out what the average of this observable is. It clearly lies between 1 and -1. It could hardly be bigger than 1 or smaller than -1. And depending on the direction of polarization, the average will just be cosine of twice the angle. You can check that out and see if it makes any sense to you by trying it out for some angles and seeing if it makes sense. But we could do the same thing with any observable. We could and any observable and any vector, we could calculate not the probability, but the average of the observable. I will use the standard terminology and call it the expectation value, but keep in mind that that really is a misnomer. It should be just the average value. Good. I think we're finished for tonight.
The preceding program was brought to you by Stanford on iTunes U and is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at itunes.stanford.edu.